Hello, we are Team B6, and this is our presentation of a proposed rainwater harvesting system for residential implementation. First, take a minute to familiarize yourself with the outline for our presentation today. We will first clarify our objective, then proceed on to specifics of our proposed system. And finally, we will justify our system's sustainability and long-term efficiency. Rainwater harvesting has been shown to be a sustainable and effective way of supplying households with pure water for consumption. It can reduce the demand on municipal water supplies, which can be especially important when rain is scarce or dry spells occur. Rainwater harvesting requires less energy to provide water to households, thereby decreasing carbon emissions. Using solar panels, as you will see later, to power the required components further reduces the GHG emissions of a rainwater harvesting system. After analyzing average water consumption values for two-person homes in both Canada and the United States, our team found an average of 440 liters of water is used every day, for both consumption and other tasks, such as watering plants, washing dishes, and doing laundry. The maximum cost this project is allowed to reach is $100,000. However, we will get to the actual cost of the project later on in this presentation. While talking to stakeholders in this project, key specifications noted were cost, reliability, and sustainability. For our proposed solution, we use a full roof catchment around 100 meters squared, as this is the cheapest per liter method of obtaining the maximum potential water collected. We also opted for 50 meters squared of additional catchment to help supplement the amount of rainwater caught on the roof. The collection tank we decided on was 2,500 liters, as this was adequate for consumption required. This will be placed beside or potentially behind the house for an increase in aesthetic appeal. The pump of choice was Pump A from the component selection guide. This was chosen specifically for its efficiency and high running hours. This pump versus system curve is also better when placed in robustness tests versus other potential pumps, leading it to its place in our rainwater harvesting system. For disinfection, ozone was chosen over chlorine because of the lower exposure risk to harmful chemicals, and the lower sustained cost of ozone over the 5-year time period. We opted for no storage tank, as it cut into the aesthetic satisfaction curve as well as the cost satisfaction curve. Since the cost is dictated by a function that is heavily influenced by the amount of water being held in the storage tank, this was not a feasible option. The storage tank location was determined through the highest flow rate to lowest cost per piping, and in the end, the location chosen was at the coordinates 30x, -15y, and 15z. For filter location, the placement greatly affected the number of times the pump needed to be replaced due to the increased amount of pressure required to get the catchment water from the collection tank to the storage tank. We chose to use 2 filters to increase the safety of our water, as well as reduce the long-term costs of replacing only 1 micrometer filter many times. The UV disinfection system of choice was the 50-watt system from the component selection guide. This is placed on the down line in order to reduce the number of times the pump on the up line would need to be replaced. This also ensured that the water was completely treated before entering the residence. This water can now be used and do any task, including drinking, washing dishes, bathing, washing clothes, and more. A critical part of the rainwater harvesting system is the electricity to power vital components such as the pump, ozone injection treatment, and UV purifier. The water pump does not always need to be on, and same with the ozone injection. However, the UV purifying system must be on at all times to ensure the water is safely treated before consumption. The UV purifier is a big energy drain on the system, so when our group was testing the amount of electricity that would be required, a choice had to be made between either a diesel powered generator or solar panels and an AC-DC converter. The diesel system was found to produce too much GHG emissions for the project to be approved, even after alternative systems such as chlorine and lower wattage UV systems were tested. Solar power was then tested, and after many reconfigurations and robustness tests, using 10 HES 260 solar panels would render the highest overall satisfaction. These 10 solar panels work in tandem with 2 2,000 watt-hour batteries to supply the pump, ozone injection system, and UV system with more than enough power for all the days of the year. Through testing many different configurations of the rainwater harvesting system, we were able to narrow in on the best solution for the stakeholders. Our first test included getting rid of additional catchment. However, this led to a significantly higher number of days where consumption values were not met. This configuration would not be viable. The next item we tested was switching the filters from the downline, as our initial intention, to the upline in order to increase the on-demand flow rate at the house. This, however, required the pump to be changed more frequently, causing an unnecessary increase in price and a minimal increase in on-demand flow rate at the house taps. The final major alternative configuration we tested was swapping ozone for chlorine. This was in order to reduce the GHG emissions of the diesel generator, After final tests were done, however, the generator was not included in the proposal, so this turned out to be an unnecessary test. Our estimated costs over the course of 5 years are roughly $39,000, accounting for a variety of maintenance and replacement costs, as well as the initial capital required to build the rainwater harvester at the desired location. Our dynamic Excel spreadsheet method allowed us to calculate the robustness tests of pump changes, swapping ozone for chlorine, and diesel-powered energy generation for the solar panels quickly and efficiently. Stakeholder satisfaction was one of the key metrics we could assess to ensure our system was not only meeting requirements, but also keeping our stakeholders as pleased as possible with the new system. As you can see, reliability and cost categories both scored very high in satisfaction. To conduct risk assessments of the proposed solution, we used a risk matrix. This is a relatively simple method in which the frequency of an event is multiplied by the severity of its consequences in the case it goes wrong. We analyzed the risk involved with reloading the generator with diesel every time it ran out, as well as the risk involved with shipping in chlorine for water disinfection. We'd never use diesel or chlorine in the end, but we have listed the risks just in case. The main focus of the rainwater harvesting system was to keep initial costs and long-term costs low, as well as having a reduced maintenance load over the next 5 years, all while providing the consumption required by the stakeholder. This sustainable proposition should have the stakeholder paying the minimum amount of money for a reliable and efficient rainwater harvesting system. Through robustness tests and many alternative configurations, we narrowed in on the most cost-effective yet reliable solution. Building a dynamic Excel spreadsheet allowed for quick testing of new configuration ideas and simple component swapping, reducing the time on our end of finding the most tangible rainwater solution for the stakeholder. Here's a list of websites we referenced in our presentation. Thank you for listening.